Hello students, so in the previous class we have discussed about the attributes with equal frequencies and unequal frequencies of chi-square test. Now in this the last topic is here chi-square test for goodness of fit. So what is this goodness of fit here? So for the given data just we have to prove that binomial distribution is a good fit or the Poisson distribution is a good fit here. So if you see the problem here, a set of 5 similar points is tossed 320 times and the result is number of hits, that is 0, 1, 2, 3, 4, 5, and the frequency is 6, 27, 72, 112, 71 and 32. So test the goodness of fit, and the chi-square tabular value for 3 degrees is here 7.81. Now whenever the question means the experiment of tossing a coin or rolling a dice comes, so ultimately we have to depend on binomial distribution. So here test the goodness of fit means we have to prove that binomial distribution is a good fit here. So the null hypothesis will be binomial distribution is a good fit. Against alternative hypothesis, binomial distribution is not a good fit. Then under the null hypothesis, the test statistic is given as chi-square equal to summation of observed minus expected frequency whole square by expected follows a chi-square with n minus k minus p degrees of freedom here. So here n represents the total number of observations, L is the linear restriction, k is the number of parameters estimated and p is the number of degrees of freedom lost due to pooling. Now first here if we are fitting the binomial distribution, we have to know the values of n and p. So for binomial distribution fitting, the n value is here 5 trials are there, but here we have to estimate the value of p. So to estimate the value of p, first we have to just find the mean of the given data here. So that can be found. So it is consider this number of heads as x here. So 0, 1, 2, 3, 4, 5. And the corresponding frequencies are 6, 27, 72, 112, 71 and 32. Now we have to find the f into x here. So f into x means here 0, 27, 144, then 336, then 284 and here it is 160. Now find the total frequency and the summation f into x here. So total frequency is 6 plus 27 plus 72 plus 112 plus 71 plus 32 is equal to 320 here. So the total frequency is denoted by capital N and the number of trials are denoted by small n here. Then f into x is here 27 plus 144 plus 336 plus 284 plus 160, it is 951. Now whenever the data is given like this, we have to find the mean of the given data by using the formula summation f into x by summation f, where summation f is nothing but capital N here. So this is 951 by 320 is equal to 2.9719. Now we know that the mean of the binomial distribution is here NP. Now equate the mean of the given data to the mean of binomial distribution. Then x bar equal to NP. So we know the x bar value, we know the n value. Now from this here p equal to x bar by n. That means 2.9719 by 5. So this is equal to here 0.59. So when p is equal to 0.59, q is nothing but 1 minus p. So 1 minus 0.59 is equal to 0.41. So we got the p value, q value. So from this we can just frame the probability mass function of binomial distribution. So after finding the p-value and q-value, the probability mass function of binomial distribution is 5cx into 0.59 power x into 0.41 power 5 minus x here. Now using this probability mass function, we have to obtain the probability of 0, 1, 2, 3, 4, 5. Then from that, we have to obtain the expected frequencies. So in the calci, we have to give the equation as 5cx into 0.59 power x into 0.41 power, open the bracket, then again give the 5 minus x. So this concept of this calci operations we have learned in unit 2 here. So let us take the tabular form again. 0, 1, 2, 3, 4, 5. The frequencies which are called the observed frequencies are 6, 27, 72, then 112, 71 and 32. Then next we have to obtain the probability of xi, then expected frequency, then observed minus expected frequency whole square by expected here. Okay. So let us take the equation. So 5cx 0.59 power x 0.41 power 5 minus x. Now press the calci key. It is asking x value. Give the value 0. So it is here 0.0116. Again press calci and give the value 1. 0.0834, then 2, 0.2399, then 3, 0.3452, then 4, 0.2484, and then for 5, 0.0715. Now for all these here, we have to obtain the expected frequency, which is given by the formula 320 into p of x here. So 320 into x. So for that also we can use the calci operation. X means here 0.0116. It is 3.712. Then 0.0834. 26.6. Then 0.2399, 76.76, then 0.3452, 110.46, then 0.2484, 79.48, and 0.0715, 22.88. Now here all the expected frequencies must be greater than or equal to 5 here. Now here one of the expected frequency is less than 5. Now we have to add this with the below one. Then it becomes greater than 5 here. So if you add that is 3.712 plus 26.68 becomes 30.392 here. 30.392. So whatever we are adding, the same corresponding observed frequencies also we have to add. Now this is here 33. Okay. Now we have to use the formula observed minus expected frequency whole square by EI here. So for that again we have to use the calci operation as x minus y whole square divided by y, where x is here the y and y is here EI. So that is here x minus y whole square divided by y. Now x means here 33 observed frequencies, y means 30.392, so it is 0.2238. Okay, then next again press calci, it is 72. Y value is here corresponding 76.76. So it is 0.2952. Next 112 x value corresponding expected is 110.46. 0.0215. Then next, observed is here 71. The corresponding expected is 79.48. So 0.9048. The last one is here 32. The corresponding expected is 22.88. So it is 3.6352. Now we have to add all these OI minus EI whole square by EI here. So these are the OI minus EI whole square, right? So this is here 0.2238 plus 0.2952 plus 0.0215 plus 0.9048 plus 3.6352. So the chi-square calculated is here equal to 5.0805. Now coming to the tabulated value here, so chi-square tabulated at n minus L minus k minus p here. So we know that n is already equal to total number of observations. For fitting a binomial distribution only, the n value will be equal to 5, but for tabulated value it is 6. And n is always 1 only. We have only one linear restriction. The sum of the observed must be approximately equal to the sum of the expected. Then here k is the parameter estimated. We have estimated the parameter p, so it is also equal to 1. And p represents the frequencies which are less than 5. So here we have pulled here two observations. That is p value is here 1. Okay. So the 3.712 is less than 5 here. So at 6 minus 1 minus 1, for the level of significance is not mentioned in the question for 5%. So 6 minus 1, 5 minus 1, 4, 4 minus 1, 3. So chi-square 3 is here 7.81. So chi-square calculated is 5.0805 and chi-square tabulated is here 7.81. So that means chi-square calculated is less than chi-square tabulated. So therefore H0 is accepted. H0 is accepted means here binomial distribution is a good fit. Binomial distribution is a good fit here. So that is the conclusion for this problem. So remember here, if any of the expected frequency is less than 5, if you are adding with the below one or the above one, whatever we are adding here, the corresponding same observed frequencies also we have to add. So that is the condition you have to remember here. Okay, so this is about this binomial distribution for goodness of fit. Now let us see the problem on Poisson distribution. Feed a Poisson distribution to the following data and test for its goodness of fit at level of significance 0.05 and the tabulated value is given as here for 3, that is 7.81. So if suppose directly the question is not given that to test the goodness of fit for Poisson distribution, instead of that they have given some number of printing mistakes in a book, or the number of fishes drawn from a lake, the number of telephone calls received in a particular interval of time, and test the goodness of it they ask. That means you have to use the Poisson distribution. Now the null hypothesis is here Poisson distribution is a good fit. Then against alternative hypothesis, Poisson distribution is not a good fit. Then under the null hypothesis, the test statistic is given as here chi-square equal to summation of observed minus expected whole square by expected follows a chi-square with n minus L minus k minus p. So here n is here, total number of observations are here 5. Okay. Now again, just like the binomial distribution, here also we have to find the mean of the given data, which is given with the formula summation f into x by summation f here. So here we have x 0, 1, 2, 3, 4 and frequencies as 419, 352, 154, 56 and 19. Now f into x means 0, 352 and this is here 308. Then 56 into 3 is here 168 and 19 fours is 76. Now find the total of the frequency and f into x here. So 419 plus 352 plus 154 plus 56 plus 19 is equal to 1000. Now this is here 352 plus 308 plus 168 plus 76 is equal to 904. So that means here x bar is 904 by 1000 is equal to 0.904. But we know that the mean of the Poisson distribution is here lambda. So equate that. So it is here x bar equal to lambda. That means lambda value is 0.904. Then the probability mass function of Poisson distribution is here e power minus 0.904 into 0.904 power x by x factorial. Right? So we have to obtain the probability of 0, 1, 2, 3, 4. Now first we have to find e power minus 0.904. So for that use the shift away. Then within a bracket minus symbol 0.904 is here 0.4049. 0.4049. Now in the calci, this e power minus lambda is common for all x values. In the calci, give the equation as 0.4049 into 0.904 power x whole divided by x factorial. So this bracket is only for lambda power x and these brackets are entire numerator. Now give the equation in the calci. For factorial we have to use the symbol shift x symbols. Okay. Now press calci key. It is asking 0 x value, so give 0. So p of x. That is 0.4049. Then press calci, get a value 1, 0.366. Then again press calci, get a value 2, 0.1654. Again press calci and get a value 3, 0.0499. Then again press calci and give the value 4, 0.0113. Now next we have to obtain the expected frequency, which is nothing but n into p of x, means 1000 into the corresponding probabilities. So it is 404.9, it is 366, 165.4, 49.9 and 11.3. So all the expected frequencies are greater than 5 only. So that means here p value is equal to 0. Now directly calculate the observed minus expected whole square by expected. So it is for that again use the equation as x minus y whole square divided by y, where x is observed and y is here expected. Right? So now press calci, it is asking x value. X value means here these frequencies, because these are called the observed frequencies. So 419 and press equal to, it is asking y value. Y value means 404.9, 0.491. Now again press calci. Now this value is here 352. Then 366 is the corresponding expected frequency. Now the value is 0.5355. Now next observation is here 154. Corresponding expected is here 165.4. So 0.7857. Next 56. and here it is 49.9.7457. Last one is 19 and here it is 11.3. So 5.2469. Now add all these observations here. So 5.2469 plus 0.7457 plus 0.7857 plus 0.5355 plus 0.491 is equal to 7.8048. So this is our calculated value. Now we have to obtain the tabulated value at n minus L minus k minus p here. So chi-square tabulated at n means here total number of observations are 5. So 5 minus 1 minus, we have estimated the lambda value, so minus 1 minus 1 expected frequencies are greater than 5 here. So it is for 5%. 5 minus 1, 4 minus 1, 3. So chi-square 3 is here 7.81. So chi-square calculated is 7.8048 and chi-square tabulated is 7.81. So that means chi-square cal is less than chi-square tab. So therefore H0 is accepted. H0 is accepted means here Poisson distribution is a good fit. Okay, chi-square tab is 7.8048 and chi-square tab is 7.81. So if the calculated value is less than or equal to calculated value, H0 is accepted here. So that's about the goodness of fit. So with this we have completed the fourth unit, that is testing of hypothesis. I hope you understand these problems.